What you just heard was sound from very different things with very different pitches, or sound frequencies. Every day, we wander the earth and hear sounds of very different pitches and frequencies. Our ability to perceive sound and pitch plays a very important part of our lives. It allows us to hear the large differences in machines to the subtle inflection in people's voices during conversations. So how are we able to hear these differences in pitches and frequencies of sound? Well, to begin to understand the complex nature of this ability, let's take a look at what sound really is and how we hear sound. Sound is simply energy made of waves of vibrations. The faster the waves vibrate, the higher the frequency. There is a massive range of sound frequencies, and the human ear can only detect between 20 to 20,000 Hz. So how do our ears detect this? Our ear is composed of a three-part structure, the outer, middle, and inner ear, each with different roles. The outer ear consists of a pinna or auricle and the external auditory canal. It also contains the tympanic membrane, in other words, your eardrum, which sits at the very end of your ear canal and is responsible for receiving sounds by vibrating. The vibrations that the eardrum picks up is then transferred through a three-bone structure within the middle ear, made up of the malleus, incus, and stapes, which amplifies the incoming sound vibrations. These vibrations then get sent to the cochlea within the inner ear. This is where the vibrations get detected and sent to the brain for interpretation. So, how does the cochlea work? Let's take a closer look. The cochlea is a small structure shaped like a snail that is filled with fluid and is split into two sections by the basilar membrane and elastic partition. The cochlea serves as the base where the main structure of hearing sits. So as the sound vibrations enter the ear, it causes the three bones in the middle ear to vibrate, which then amplifies the vibrations through the cochlea. This movement of the bones causes the fluids in the cochlea to ripple. The ripple of the fluid in the cochlea causes the hair cells sitting on the basilar membrane to move, which then sends a signal known as an axial potential to the brain for interpretation through the auditory nerve. That is essentially the simplest picture to how we hear sounds. But that isn't the reason we are here. We want to know how we perceive different pitches, which isn't the same as frequency. Frequency is a scientific measure of pitch, and it is fixed for each type of sound. Sound waves don't actually have a pitch. Instead, pitch is a brain's interpretation of the sound frequencies. We currently have two theories to explain this fascinating ability of pitch perception. The first theory is the temporal theory, which assumes that the frequency is coded by the activity level of the sensory neurons. This means that if we have a particular hair cell, it will only send a signal to the brain when a specific frequency of sound wave triggers this particular hair cell. This is a pretty good explanation of how we are able to hear different pitches of sounds. The theory is quite intuitive. However, our ears detect such a wide range of frequencies that it will be very hard for every hair cell to account for all the frequencies and fire at a rate so that we can hear. There will be a point where a hair cell for a specific frequency cannot fire any faster to keep up with how quickly sound is being detected by our eardrum, meaning we will not be hearing the true nature of sound. Imagine a drummer drumming really fast. If this theory is true, we may not be hearing every single beat of the drum. So how could we hear different frequencies if the temporal theory isn't the best possible explanation? Well, scientists have suggested that different portions of the basilar membrane are sensitive to different sound frequencies, where the apex of the basilar membrane is most sensitive to low frequencies and the base to high frequencies. This is called the place theory, because the detection of each sound frequency depends on where it peaks along the basilar membrane. Based on the place theory, this also means that our hair cells and nerve fibers have the same selectivity for each sound frequency. This property is known as the characteristic frequency. It is also why many people with damage to their hearing cannot hear certain frequencies. Now, both theories describe different aspects of pitch perception, and both are needed. Sounds with frequencies below 4000 Hz rely on both the temporal and place theory, whereas the place theory has a larger contribution to pitch perception with higher frequencies. So we really cannot say one is better than the other, because they aren't, but they do complement each other. and both are correct in one way or another. Another thing that we know that is also important is how we know where each sound we hear is coming from. Without this ability, we would be pretty disoriented on a daily basis. So how is it exactly that we are able to tell where each sound is coming from? Our auditory system uses two mechanisms to determine the original source of every sound: monaural and binaural cues. Monaural cues are intended to determine and locate sounds occurring in front, behind, above, and below us. Without this ability, we would be very confused about where sound is coming from. Let's imagine hypothetically that we were blindfolded and there was a dog barking in front of us and behind us, taking turns barking. Without mono hearing, the barks would sound identical and we wouldn't know if there was a dog in front of us or behind us. Monaural hearing allows us to differentiate between the dog barking in front of us and behind us because the sound interacts with the pin of our ear differently relative to where the sound is originating from. We also have binaural cues, which helps us to locate sound along a horizontal axis and relies on the patterns of vibrations of the eardrum between our left and right ear. This ability relies on two main principles. Let's return back to the hypothetical situation of the dogs barking, but instead we have one dog barking on the right. The bark we will hear will be more intense on the right and will dissipate when it reaches our left. This is known as interaural level differences and allows us to locate whether the dog is barking on the left or the right based on the intensity of that sound, because eventually the sound will reach both our ears. The other principle is known as interaural timing differences. It's similar to the interaural level differences, but relies on the fact that the sound originating from the left or right will reach both our ears at different times. In the case of the barking dog analogy, the bark will reach our right ear before our left. This allows our brain to monitor and locate where along the horizontal axis the sound is coming from. So the human ear is a fascinating structure that allows us to perceive different pitches in sound and locate where the original source of the sound is coming from. Without it, we would live life in confusion and disorientation. Just imagine if we live life not knowing where sound is coming from. We wouldn't know where our friends are saying hello, or even worse, where a lion is, putting us in danger. Thank you for staying until the end of this video. Hopefully you found this topic of pitch perception interesting and learned something new. If you like more videos like this, make sure to smash the subscribe button to show us your support. Feel free to give any topic suggestions in the comment section down below. And as always, we are the ones that wonder, so keep on learning and keep on wondering. See you all next time!